Yes. Welcome to my channel. This is Rekha Venkateshwarlu, Assistant Professor of Physics, Government Degree College for Women, Nalgonda. In the present class, now I am going to discuss about the topic linear and surface charge distribution under the application of Gauss law. You know, this is BSc Physics 5th semester Electromagnetism Unit 1 syllabus. Okay. So the contents of the present lecture are: the first, we will discuss the electric field strength due to the point charge. Then after applying the Gauss law to the linear charge distribution, there we will see the case uniformly charged wire. After that, Gauss law application to surface charge distribution. Example, uniformly charged infinite non-conducting sheet. And after that, uniformly charged infinite conducting sheet. Lastly, we will see the conclusions. Okay, this is the plan of my talk, right? Now, so before start of lecture, let me start with the Gauss law statement. What is that? The total normal flux over a closed surface is equal to 1 by epsilon naught times to the charge enclosed within the surface. This is the statement, right? Here you consider a charge Q. So around the charge, I consider a closed surface. Then the flux through this closed surface equal to 1 by epsilon naught times to the charge enclosed within this surface. How much charge enclosed in this surface? That is Q. So Q by epsilon naught, right? So what I am saying here, the mathematical statement for Gauss law is this one, sir. Surface integral E bar dot ds bar equal to 1 by epsilon naught times to the net charge enclosed by this closed surface. Okay, where epsilon naught is permittivity of free space. Permittivity. Suppose if the charge is assumed in the dielectric medium, then formula changes as surface integral E bar dot ds bar equal 1 by epsilon into K. Okay. So when the charge is placed or situated in the free space or air or vacuum, then we are using this formula. E bar dot ds bar represents what? This is electric flux through this closed surface. That means what? The number of electric lines of force coming out normally through the given surface. So the normal electric flux over a closed surface is equal to 1 by epsilon naught times to the net charge enclosed by this surface. This is the Gauss law statement, right, sir? Now, so using this Gauss law, let us see the applications one by one, sir. The first, how to find the electric field strength due to the point charge. Already we derived the field strength due to the point charge by using the Coulomb's inverse square law, that E equal 1 by 4 pi epsilon naught Q by R square. It is discussed in the last class, sir. Okay, in the previous class we discussed that one. So here we have to derive the same formula by using the Gauss law. How to derive? Okay. Still the people are joining. Right, sir. Now, you consider here the charge Q is placed at the point O. At the distance R, I am assuming a spherical Gaussian surface. This is a spherical Gaussian surface. Okay. So now the total flux coming out through this Gaussian spherical surface should be equal to, according to the Gauss law, how much? Q by epsilon naught. Okay. So that is I am writing here. So here the charge Q is there, sir. Q is charge is there. Now you consider a small area element here, ds bar. Small area element ds bar. Then the direction of the ds bar will be like this. That is perpendicular to this surface. Okay. But actually, what is the direction of field strength at that point? That will be in the same direction. Electric field strength direction is always normally outwards. So on the spherical surface at every point, the direction of electric field strength is like this. That is perpendicular to the surface at every point, sir. Okay. So now I consider a small area element ds. So the direction of ds, that is area, is a vector quantity, right? The direction of area vector is a ds bar, that is perpendicular to this area. Okay. So ds bar direction and e bar direction both are in the same direction. Here, this orange line represents the ds bar direction. Yellow line represents electric field strength direction at that point. So what is the angle between E bar and ds bar here, sir? That is 0 degree. Then flux through the small area element. Flux, electric flux through small area element, we write as, that is E bar dot ds bar. Okay. The flux through the small area element equal to E bar dot ds bar. That we represent with the d phi. D phi equal to E bar dot ds bar. Since theta is 0, E bar dot ds bar equal E ds cos 0, then you will get E into ds. Okay, E into ds. Now this is the small, the flux through the small area element. But the total flux through this entire surface is given by, we have to integrate this. So to get the total flux phi, we should integrate the E bar dot ds bar. So that is written here. The total surface integral E bar dot ds bar is equal to Q enclosed by epsilon naught. 1 by epsilon naught times to the charge enclosed within this spherical surface. How much that is? Q. Okay. So here left side, that equal to EDS, already have written here. Since field strength at every point on this surface is same, due to the symmetry of charge distribution, all the points on the spherical surface, are at the equal distance from the center. The magnitude of field strength at every point on the spherical surface remains constant. Since E is constant, you write outside of the integral, right? E integral of ds, closed integral of ds, how much? That is surface area of this sphere. Sphere radius r, hence surface area 4 pi r square. Hence left side we got E into 4 pi r square. So right side how much, sir? Q by epsilon naught. From this you write Q as the subject. Okay, then E is equal to 1 by 4 pi epsilon naught Q by r square. This is the expression for electric field strength due to a point charge Q at the distance r. Okay, from this it is very clear, E inversely proportional to r square, right? E bar equal to 1 by 4 pi epsilon naught Q by r square into, you can write r caps, right? So this is simply in this way you can derive the electric field strength formula by using the Gauss law, right, sir? Let us see the next application. Electric field strength due to an infinitely long charge wire, sir. This is application for linear charge distribution. Okay na? So మనం ఏం చెప్పాము, ఇక్కడ ఒక పాయింట్ చార్జ్ నుంచి ఎలక్ట్రిక్ ఫీల్డ్ స్ట్రెంత్ కి ఫార్ములాని గాస్ లాని ఉపయోగించి అప్టైన్ చేశాం సార్. సెకండ్ అప్లికేషన్ ఏంటంటే లీనియర్ చార్జ్ డిస్ట్రిబ్యూషన్ కి గాస్ లాని అప్లై చేయడం ఎట్లా, మీరు ఇక్కడ డయాగ్రామ్ ని అబ్జర్వ్ చేయండి సార్. సో దిస్ ఈస్ ద infinite length of a uniformly charged straight wire. Okay, so it is a positively charged wire. Now at the distance r, you consider the point P here. I have to find the field strength at this point, sir. Okay, now since it is positively charged, the electric lines of force due to this wire will be like this in all directions. They may be upwards or downwards or left side or right side, whatever it is. So that is perpendicular to this wire like this. This is E bar direction. Okay. To find the electric field strength at the point P, I am constructing a cylindrical Gaussian surface which is passing through this point. This is the cylindrical Gaussian surface. Clear? Now here, so you will observe the three regions. So this is the region 1. Okay, I will show that for clarification. So this is the region 1. Okay, now This is the region 2, circular regions. And the third one, this is, I will show it with another color. This is the chord surface region. There are three regions. Region 1, it is region 2, the chord surface is third region. Okay. So first you consider the region 1 cell. If you consider the region 1, it is very clear the direction of area vector, how it is perpendicular to this one in this direction, ds bar direction. Okay. ds bar direction is perpendicular to this area element. This is ds bar. But here the field strength direction is how? Here the field strength direction is in this direction. That is in this direction, E bar direction. Here E bar, ds bar are perpendicular. So therefore E bar dot ds bar equal E ds cos 90. Then you will get 0. That means what? The flux through this circular area, the flux through this region 1 is 0. Okay. నేను P వద్ద ఎలక్ట్రిక్ ఫీల్డ్ స్ట్రెంత్ ఫైండ్ అవుట్ చేయడానికి P గుండా P నుంచి పోయేటట్టుగా ఒక సిలిండ్రికల్ సర్ఫేస్ ని ఇట్లా అజ్యూమ్ చేశాను సార్. ఇవి రెండు కూడా ఎండ్స్ కదా, ఎండ్స్ ఆఫ్ ద సిలిండర్. ఈ మధ్యలో ఉన్నది సర్క్యులర్ కర్వ్డ్ సర్ఫేస్ అవుతుంది. ఇక్కడ ఈ సర్క్యులర్ సర్ఫేస్ రీజియన్ తీసుకుంటే ఇక్కడ రీజియన్ 1, రీజియన్ 2, రిమైనింగ్ పోర్షన్ అంతా కూడా కర్వ్డ్ సర్ఫేస్ రీజియన్. ఇక్కడ నుంచి మన ఫ్లక్స్, మన టోటల్ ఫ్లక్స్ త్రూ దిస్ క్లోజ్ సర్ఫేస్ అంటే ఫ్లక్స్ త్రూ ద రీజియన్ 1, ఫ్లక్స్ త్రూ ద రీజియన్ 2 అండ్ ఫ్లక్స్ త్రూ దిస్ కర్వ్డ్ సర్ఫేస్ రీజియన్. అది దట్ విల్ గివ్ ద టోటల్ ఫ్లక్స్ త్రూ దిస్ క్లోజ్ సర్ఫేస్ అవుతుంది. ఎందుకు? మనకు గాస్ లా స్టేట్మెంట్ ప్రకారం ఒక క్లోజ్డ్ సర్ఫేస్ నుంచి బయటకు వచ్చే ఫ్లక్స్ Q/ε0 ఈక్వల్. కాబట్టి హియర్ ద టోటల్ ఫ్లక్స్ త్రూ దిస్ టోటల్ క్లోజ్ సర్ఫేస్, ఎంటైర్ క్లోజ్ సర్ఫేస్ ఈక్వల్ ఫ్లక్స్ త్రూ రీజియన్ 1, ఎలక్ట్రిక్ ఫ్లక్స్ త్రూ రీజియన్ 2, ఎలక్ట్రిక్ ఫ్లక్స్ త్రూ రీజియన్ 3. ఇది మనం వేయాలి. ఇక్కడ మాట్లాడుతున్నాం ఇది స్మాల్ ఏరియా ఎలిమెంట్ ds బార్ సార్. ఏరియా వెక్టార్ యొక్క డైరెక్షన్ అవుట్వర్డ్ నార్మల్ యూనిట్ వెక్టార్ అంటే ఈ డైరెక్షన్ లో ఉంటుంది. సో దిస్ ఈస్ ద ds bar direction. Here I am writing, so ds bar direction is this one. So this is the ds bar direction. So here this is capital E direction, electric field strength direction, that one. Okay, since E bar ds bar are perpendicular, E ds cos 90 is 0 అంటే ఈ ఏరియా నుంచి లైన్స్ ఆఫ్ ఫోర్స్ ఇటువైపు పోవు అని అర్థం. ఫ్లక్స్ త్రూ దిస్ region 1 is 0. Similarly, you take here also same concept. Here the direction of ds bar is like this and electric field strength direction atla undi in this direction. This is E bar direction. Okay, so I am writing here, this is the direction of E bar. So this is the direction of ds bar. Angle between ds bar and E bar how much sir? 90 degree. Then E bar dot ds bar how much? E ds cos 90. That equal to 0. That means what? Electric flux through the region 2 also 0. Then no electric lines of force will pass in this right side direction. No electric lines of force will pass in left side direction. Only the lines of force will move in through the curved surface perpendicular to the surface in all directions. Therefore, the net flux is given by the flux through the region 3 only. Okay, so for that I am considering a small area element here at the point P. You consider a small area element ds, right? Now what is the direction of ds bar here? That is perpendicular to this one in this direction, ds bar direction. Okay, the direction of ds bar is ds bar direction this one, E bar direction same. Here E bar ds bar both are parallel. Okay, both are parallel. Then what is the dot product of this? E bar dot ds bar equal E ds cos 0. Then you will get E into ds. Therefore, the flux through the small area element ante EDS. కానీ మనకు టోటల్ కర్వ్డ్ సర్ఫేస్ నుంచి ఫ్లక్స్ కావాలి అంటే we should integrate that one. Closed integral E bar dot ds bar gives the total flux through this curved surface region. Okay, now I will go for the next Yes. The total flux is equal to surface integral E bar dot ds bar over the region 1, flux through over the region 2, flux through the region 3. Here, the first one and third one 0 because circular surface area దగ్గర flux 0 అని చూపించాను. There E bar ds bar perpendicular. So only the flux is equal to the surface integral E bar dot ds bar at the region 3, E into ds. Since E is constant, you write E outside. Closed integral ds is equal to the surface area of the cylinder 2 pi rl. Okay. So this is the total flux through the curved surface region. Right, sir? Now, according to the Gauss law, we have the expression that surface integral E bar dot ds bar equal to Q enclosed by epsilon naught. But here lambda is linear charge density, that is nothing but charge per unit length, lambda equal to Q by L, from that Q equal to lambda into L. You substitute this value here. So in the numerator have written lambda into L by epsilon naught. Then, so what you get? E into 2 pi RL is equal to lambda L by epsilon naught. Both sides L cancel. So finally, we are getting E is equal to lambda by 2 pi epsilon naught R. If you want to express this in vector form, you can write it as E bar equal lambda by 2 pi epsilon naught R into R cap, where R cap is the unit vector along R bar direction. Otherwise, you can write like this also. How we can write? So that will be written like this also. E bar equal to lambda by 2 pi epsilon naught R square into R bar. The denominator lo R square రాస్తే ఇక్కడ R bar రాయండి. Okay. So both sides magnitude తీసుకుంటే modulus E bar అంటే ఇక్కడ modulus R bar R వస్తుంది. ఒక R cancel అయితే you will get the same. లేదా ఇలాగే ఉంచాలనుకుంటే E bar equal lambda by 2 pi epsilon naught R into R cap. So if you write R in the denominator, then here you write R cap for vector form. If you want to write R square in the denominator, you should write R bar here. Okay. Here, if the infinite length of the charged wire is positive, that is positively charged, then E bar is radially outwards. If lambda is negative, that is nothing but if the wire is negatively charged, then E bar is radially inwards. Okay. So this is about applying the Gauss law to find electric field strength for the linear charge distribution. So linear charge distribution ki example em cheptunnam, uniformly charged infinite length of a wire తీసుకున్నాం. Okay, wire అంటే one dimensional కాబట్టి L length ఉన్నటువంటి వైర్ Q charge distribute అయ్యింది సార్. Then linear charge density lambda equal to Q by L. ఓకేనా? ఇప్పుడు ఈ యూనిఫామ్లీ చార్జ్డ్ వైర్ నుంచి R డిస్టెన్స్ లో R పర్పెండిక్యులర్ డిస్టెన్స్ లో ఫీల్డ్ స్ట్రెంత్ ఫైండ్ అవుట్ చేయడానికి ఒక సిలిండ్రికల్ గాసియన్ సర్ఫేస్ ని అజ్యూమ్ చేశాను. ఇప్పుడు సర్ఫేస్ మీద P అనే పాయింట్ ఉంది. ఓకే, ఇప్పుడు ఇది పాజిటివ్లీ చార్జ్డ్ వైర్ అయితే ఈ బార్ డైరెక్షన్ రేడియల్లీ అవుట్వర్డ్స్ ఉంటుంది, బయటికి వెళ్ళే డైరెక్షన్ లో ఎక్కడైనా. ఓకే, ఒకవేళ నెగటివ్లీ చార్జ్డ్ వైర్ అయితే then the direction of field strength is radially inwards. E bar direction లోపలి వైపు perpendicular to the wire ఉంటుంది. So this is the conclusion here I discussed. Okay sir. Now the next application is field due to the infinite conducting sheet. This is application for surface charge distribution. Here we will see the two applications, sir. Electric field strength due to the infinite conducting sheet. The second one, field strength due to infinite non-conducting sheet. First, we will see the uniformly charged infinite conducting sheet. You observe the figure. This is an infinite conducting sheet. Here it is positively charged. In the case of conducting sheet, charge resides only on its surface. అంటే ఒక ఇన్ఫినైట్ కండక్టింగ్ షీట్ మీరు చార్జ్ చేస్తే దాని యొక్క ఛార్జ్ ఓన్లీ దాని సర్ఫేస్ మీద మాత్రమే ఫామ్ అవుతుంది. షీట్ లోపల ఛార్జ్ ఫామ్ కాదు. ఏదైనా ఒక మెటాలిక్ స్పియర్ తీసుకోండి సార్. మెటల్ అనేది గుడ్ కండక్టర్. కాపర్ స్పియర్, అల్యూమినియం స్పియర్, ఐరన్ స్పియర్, వాట్ ఎవర్ ఇట్ ఇస్. ఏదైనా ఒక మెటాలిక్ స్పియర్ని మీరు చార్జ్ చేస్తే దాని సర్ఫేస్ మీదనే చార్జ్ ఫామ్ అవుతుంది. ఇన్సైడ్ ద కండక్టింగ్ స్పియర్ చార్జ్ ఉండదు, ఎలక్ట్రిక్ ఫీల్డ్ ఉండదు. ఓకే, హియర్ వీ కన్సిడర్ an infinite sheet, conducting sheet. When it is positively charged, the surface, the charge will reside only on its surface. Charge will be distributed only on the surface. Charge cannot accumulate inside the charged body, inside the conducting body. So that is the important point you have to notice here, sir. Right. Now my intention is I have to find the electric field strength at the nearest point. దీని దగ్గరలో ఒక P అనే పాయింట్ తీసుకున్నాను. P దగ్గర నేను ఫీల్డ్ స్ట్రెంత్ ఫైండ్ అవుట్ చేయాలి. ఓకేనా? సో దానికోసం ఏం చేశాను, ఐ assumed a cylindrical Gaussian surface. Right. So now the point P lies on this Gaussian surface. Okay. So here the direction of this small area element. So this is some circular end, this is the circular end left end, yeah, this is right end also circular region. The remaining portion is this total curved surface region. And what is the total flux here, sir? The total flux through the closed surface and flux through the left end, flux to the right end cap, flux through the curved surface. Okay, now the first you consider the right hand, sir. At the right end, what is the direction of ds bar? This is the direction of ds bar. Okay, but the direction of electric field strength due to the positively charged plane sheet is always normal to this sheet one. Electric lines of force will be like this, normal to the sheet, outward direction, away from the sheet. So at this position, when we talk at this point, here E bar direction, ds bar direction same. Then what is the flux through this small element? E bar dot ds bar, that is called E ds cos 0. You will get E into ds. So electric flux through small area element d phi equal to E into ds we got, sir. But what about the left hand? Charge is residing only on the surface, this surface. There is no charge on the back side. Here no charge, therefore no field here, no flux here. Electric flux coming out through this left hand is 0. Here no flux linking with this surface. Okay. So what about the curved surface? You consider a small area here, ds bar. Then the direction of the ds bar will be like this, perpendicular to this one. This is the ds bar direction. Okay, but the field strength direction is towards right side, that is perpendicular to the sheet. So what is the angle between E bar and ds bar here? That is 90 degree. So what is the flux through this small area element? EDS cos 90. How much that's value? 0. Flux through small area element E bar dot ds bar equal to 0. Therefore no lines of force will move in this direction or in this direction or perpendicular to this curved surface in any direction. Only the flux through this small circular area element, that is right and right cap end cap, contributes the net flux in this case. Okay, so now let us see that one. Okay, so we will write the total flux through the curved surface is equal to the flux through the right end, the flux through the left end circular region, and the electric flux through the curved surface region. So here it is 0, right? Only this is contributing the total electric flux, the net electric flux. Since E ds cos 0, you write E outside. Closed integral ds is nothing but the surface area of that circular region. Yes, phi equal to E into S. Okay, so now finally what we got? Phi equal to E into S is the total flux through that closed surface. But according to Gauss' law, that total flux should be equals to Q by epsilon naught. But here Q equal to sigma into S. Why? Because sigma is the surface charge density, that equal to charge by area. Sigma equal to Q by S. Then you will get Q equal to sigma into S. Substituting here, so both sides S cancel. Finally, we are getting E is equal to sigma by epsilon naught. This is the expression for electric field strength at the nearest point of uniformly charged conducting sheet. అంటే ఏదైనా ఒక కండక్టింగ్ షీట్, ఇన్ఫినైట్ కండక్టింగ్ షీట్ ని మనం చార్జ్ చేస్తే దాని సర్ఫేస్ మీదనే చార్జ్ ఫామ్ అవుతుంది సార్. ఓకే, ఇప్పుడు ఇది పాజిటివ్లీ చార్జ్ అయితే ఎలక్ట్రిక్ లైన్స్ ఆఫ్ ఫోర్స్ పర్పెండిక్యులర్ టు ద షీట్ ఈ డైరెక్షన్ లో ఉంటాయి. కాబట్టి దీని నియర్ గా ఉన్న ఎనీ పాయింట్ ద ఫీల్డ్ స్ట్రెంత్ magnitude sigma by epsilon naught, the direction is normally outwards. Suppose if this infinite conducting sheet is negatively charged, then the lines of force will be normal to the sheet towards itself. Then the field strength at the nearest point, magnitude sigma by epsilon naught, the direction is perpendicular to the sheet towards the sheet. Sigma by epsilon naught into n cap rastam. So that is how to understand. Okay, sir. Now, let us see the third application. Electric field due to the infinite non-conducting sheet, sir. So, ఇందాక మనము కండక్టింగ్ షీట్ గురించి మాట్లాడి ఇప్పుడు నాన్ కండక్టింగ్ షీట్. Consider a infinite non-conducting sheet which is positively charged. Then the lines of force, electric lines of force will be perpendicular to the sheet like this in both directions. So towards right side, the electric lines of force will be like this. Towards left side, the electric lines of force also perpendicular to the sheet like this. Okay. Now to find the electric field strength at the nearest point, that is at this point, I am considering the cylindrical shaped Gaussian surface. You can see in the figure, right, sir? Here, how many regions? So this is the region 1, circular region 1. Okay, I will show that. This is the circular region 1. Okay. Here also circular region 2, number 2. The remaining is the curved surface region. So this is the 3 and 4. 1, 2 are the circular regions. That is the ends of the cylinder. The third and fourth are curved surfaces, right side and left side regions. Then the total flux through this total entire Gaussian cylindrical surface is equal flux through region 1, flux through region 2, flux through region 3 and flux through region 4. Okay, so this is the basic concept we have to understand. So first you take this region 1, sir. At this what is the direction of electric field strength? What is the direction of electric field strength? That is the direction denoted by the yellow line. But the direction of ds bar is in this direction. This is ds bar direction. Here ds bar, e bar are in the same direction. Therefore, the flux through small this circular region e bar dot ds bar equal e into ds. Similar here also, e bar ds bar in the same direction. Ds bar direction towards left. The electric field strength direction towards left. An angle between e bar ds bar is 0 degree. Then e bar dot ds bar equal e ds cos 0. Then you will get e into ds. E into ds. Okay, the total flux is equal to es here. Here the total flux through this region e into s. Through the small area element ds, e into ds. So then the total flux through this circular region, surface integral of e ds, you will get es. Here also es. But whereas coming to the region 3 and region 4, there the direction of field strength is, the electric field strength direction is towards right or towards left here. Here ds bar direction is like this. Ds bar direction is perpendicular to e bar. Here also ds bar direction is perpendicular to e bar. Therefore, there is no flux through this curved surface. Ante only electric lines of force ఇటువైపు right side పోతున్నాయి, left side పోతున్నాయి. అంటే ఇక్కడ సర్క్యులర్ రీజియన్ 1 నుంచి మాత్రమే ఫ్లక్స్ రైట్ సైడ్ క్రాస్ అవుతుంది. ఇక్కడ రీజియన్ 2 నుంచి లెఫ్ట్ సైడ్ క్రాస్ అవుతుంది. రిమైనింగ్ కర్వ్డ్ సర్ఫేస్ థర్డ్ నుంచి ఇటువైపు ఫ్లక్స్ పోవటం లేదు, కింది వైపు పోవటం లేదు. సో కర్వ్డ్ సర్ఫేస్ నుంచి ఫ్లక్స్ లింకింగ్ 0. ఓన్లీ ద సర్క్యులర్ రీజియన్స్ 1 and 2 నుంచి మాత్రమే ఫ్లక్స్ ఉంటుంది. ఓకే, so that is the concept you have to understand here. Now from that we are writing the total flux through the entire cylindrical surface equal flux through region 1, flux through region 2, flux through region 3, electric flux through the region 4. As we discussed, the surface integral E bar dot ds bar over region 30 over region 40. These are the curved surface regions. Their E bar ds bar perpendicular. Hence E bar dot ds bar we are getting 0. Then only the flux through region 1 and 2 contribute the net flux. Therefore, surface integral E bar dot ds bar is equal to the flux through region 1 and flux through region 2. That is ES plus ES equal to 2 ESL. Okay, 2 ES. Therefore, surface integral E bar dot ds bar equal, according to the Gauss law, what we have, that is Q enclosed by epsilon naught. Left side what we got? Left side we got 2 ES, that equals sigma S by 2 epsilon naught. Here Q equal to sigma S substituted. Left side S, right side S cancel. Then finally we are getting E is equal to sigma by 2 epsilon naught. You have to understand that, you have to notice that in the case of uniformly charged conducting sheet, the field strength at the nearest point sigma by epsilon naught we got there. But here field strength is sigma